Hi there, you're welcome back to my channel. In this video, I'm going to take you through symmetric positive definite matrices. In order for you to perform Cholesky decomposition, the matrix should be a symmetric positive definite matrix. But how do you determine it? And that is what I'm going to take you through in this video. Please, if this is the first time you're being on this channel, kindly subscribe to support and don't forget to watch the videos you end. So let's break this into different pieces. Okay, so let's consider first the symmetricness. Okay, then after we go for the positive definite, right? So what is a symmetric matrix? Symmetric matrix. So when you say a matrix is symmetric, all that they are trying to say is the matrix A will be equal to its transpose. So if I have a matrix here, A, B, C, D, E, F, G, H, I. Let's say something like this. When you say this matrix is symmetric, then it means that when I take any of these rows, it should be the same as what? 8 columns. When I take this row, it should be like the second column. When I take the last row, it should be like the what? The last column. So that is a symmetric matrix. That is a symmetric matrix. So whatever row you take, if it's the first row, it should be the same as the first column. So let's see some example of a symmetric matrix here. So 2, negative 1, 0, negative 1, 2, negative 1, 0, negative 1, 2, right? So let's analyze this matrix. Okay, so when we analyze this matrix, you realize that when I take the first row, I have 2 here, I have negative 1, I have 0, right? And it's the same as my column, first column, 2, negative 1, 0, 2, negative 1, 0. So when I take this second row, it's the same as my second column. So as I said, the definition for symmetric matrices is that when you take A, it should be equal to what? A transpose. That's transpose of A. So this is a condition as I've written here. So when they give you any matrix, just take the transpose of the matrix, and if they are the same, I mean A and A transpose are the same, then you say that this matrix is what? A symmetric matrix. So that's all for the symmetric. Now let's see positive definite matrix. What do you mean by positive definite matrix? So before you can perform your Cholesky algorithm, as I said, you need to know that this matrix given is what? A positive definite matrix. So how do you do that? So test for positive definiteness. Positive definiteness. Right. So the first test is simply one, existence of all positive pivots. Existence of all positive pivots. Right. So if they give you any matrix and you want to test if the matrix is a positive definite matrix, then all the pivots of the matrix should be what? Positive. Okay. Now what do you mean by pivots? Pivots. So a pivot. So this is the first non-zero entry. Okay, the first non-zero entry in a row. So whenever I give you any matrix and a matrix, let's say 2, 1, neg 3, 5, 0, 0, 5, neg 1, neg 4, let's say 15, then 12. So when I take this matrix into consideration, for you to identify all the pivots, the pivot is what? The first non-zero entry in a row. So when I take the first row, we realize that 2 is what? Non-zero, and it's actually the first element of this row. When I come to the second row, the first non-zero is what? 5. So this happens to be my pivot. Likewise, at the third row, this happens to be my pivot. So the condition to test for positive definiteness is what? Existence of all positive pivots. So your pivot should be what? Positive before you classify it as what? A positive definite matrix. And even from the matrix I've given as an example, you realize that 2 is positive, 5 is positive, but negative 4 is less than 0 or is negative. So this can't be a positive definite matrix. So let's consider this matrix. Let's say 1, 2, 3, right? Or 0, 0, 1, 0, 4, 1, 4, 1. So this matrix, what are the pivots? From row 1, the first pivot is what? 1, right? The first pivot is 1. From row 2, the first pivot is this, and row 3, the first pivot is this. So you ask yourself, are these all greater than 1? Or sorry, are they all greater than 0? Or are these all positive? Yes, they are. Hence, this matrix from this particular condition, we can say is a positive what? Definite matrix. Okay, but it has to satisfy different conditions. So this is just the first condition. Okay, this is the first condition. So once you identify that all the pivot elements are greater than 0 or are all positive, then we move to the second test. So what's the second test? So for the second test, we are going to use the determinant. So determinants of all upper left sub matrices are positive. So right now I have some new key terms here. I have the sub matrices here, then probably maybe upper left, but it's just an English word. So the second criteria is for you to identify the determinants of all the odds upper left sub matrices, and if they are positive, then you can say that our matrix is positive what? Definite matrix, right? So let me show you what the sub matrices are. So what you are given any matrix, okay, let's say A, B, C, okay, D, E, F, G, H, I. When we are talking about the upper left sub matrices, all that we are trying to say is this is one matrix on its own. Then we come to the second matrix, which is this. Then finally, the overall matrix. So within this 3 by 3 matrix, you can get 3 sub matrices. So the first one will be a single entry. It's like a constant. So it's A. Then the second one is this 2 by 2. Okay, the 2 by 2. And we're talking about upper left. Okay, upper left. So when you take the principal diagonal of any square matrix, we have upper and lower, right? Yeah, so we are dealing with the upper left. We could have started with what? C and what? We could have started with this side too and maybe come back for the conditions of positive definiteness. We are only interested in what? The upper left side of what? The matrix. So you start from A, then you come to the 2 by 2 matrix covering what? This side, then finally the entire matrix. Those are the sub matrices of any given matrix. So if it had been a 4 by 4 matrix, it would have been this, that in that manner, right? So we have to determine the determinant. So first of all, you find determinant of A, it should be greater than 0. Determinant of what? A, B, D, E. It should also be greater than 0. Then you find the determinants of the entire matrix. D, E, F, G, H, I, right? It should also be greater than 0. So once all these conditions are satisfied, then it is a positive definite what? Matrix. Then finally, one last test which you can do, which is you can choose to, right? So this number 2 is, I mean, the determinant is one short test. Okay, once you get that, it's positive definite. But if you really want to use a different approach, then there is another approach which we use the words eigenvalues. Okay, you just find the eigenvalues of the matrix. Eigenvalues of the matrix. So what we are trying to say is every positive definite matrix, every positive definite has positive eigenvalues. They will have positive eigenvalues. So you can find the eigenvalues of the matrix, Then after you compare, if they are all greater than 0, then you can say that they are, you can say the matrix is what, a positive definite matrix, right? Yeah. So these are the few criteria. So now let's take this particular question here. So determine if the matrix below is a positive definite matrix, right? So the matrix is giving us 2 neg 1 0 neg 1 2 neg 1 0 neg 1 2. Okay, so first of all, what do? We have to go by what, the pivot test. So I'll come to my matrix and I ask myself, what are the pivots in this, what are all the pivots in this matrix? Okay, what are all the pivots in this matrix? So the first row, I'll have 2 here as what, my pivot, right? So 2 here as my pivot. When I come to the second row, I'm going to have the first non-zero entry is this one. Then when I come to this side, this is the third non-zero entry. This is also 1. So in this test, you realize that this matrix will fail to be what? The positive definite matrix. Okay, in this test, it will fail to be a positive definite matrix, right? So normally, actually, if you want to use a positive definite matrix, one condition is that you need to convert it to the reduced row echelon form. Okay, that is one condition which I left out. So before we can find if this matrix is a positive definite matrix, we need to convert this matrix into the reduced row echelon form, which happens to be the same as what, the upper triangular matrix, right? The upper triangular matrix. So we don't want to go through that stress now. So we will just simply use the determinant approach. So 1 2 then 0 negative 1. So since we don't want to use the pivot test, we can go through that approach too, but you just have to reduce this into an upper triangular matrix before you just take the pivot. Okay, before you take the pivot, right? So now let's see the second approach using the determinants. So I'll first take my first submatrix here and I'll take the determinant of 2. So the determinant of 2 is simply equal to what? 2, right? Then I'll take my second submatrix, which is 2 neg 1 negative 1 2. So what's the determinant of this? 2 by 2 minus negative 1 by negative 1. This is 4 minus 1, giving me 3. And indeed, this is greater than 2. This one is also greater than 2. Then determinant of the entire matrix. Okay, determinant of the entire matrix. So when I take 2, I'll have 2 open brackets. When I take 2, it will cancel this, right? So 2 by 2, 4. So 4 minus what? Obviously 1, negative 1 by 1, right? Then here I'll get minus 1. So plus 1 open brackets. I'll take this whole thing, this whole out. So I have negative 1 by 2 minus 0. So minus 0 will go. Then the rest will be 0 times, so to go. So I have 2 multiplying 4 minus 1 plus negative 2. And this is going to be 6 minus 2, which is 4. And 4 is greater than 0, right? So now you realize that from the determinant test, the determinant of all the submatrices, upper left submatrices, are all greater than 0. So our matrix here is a positive definite matrix. It's a positive definite matrix. Take note. So clarifying the initial pivot test, as I said, it's you have to first convert it to row echelon form or the upper triangular matrix. So you realize that from the initial examples I gave, they were all in what? The reduced form. So please take note of that. So it is the first non-zero entry in the row echelon form or reduced echelon form to be specific. Okay, so this is all I have for you in this video. Please don't forget to subscribe, like, and share to get more useful contents like this.